The moment you find the most boring number in the world, that number stops being boring. There are no scary equations here. Just 3 tools: lining numbers up, counting them, and a small computer experiment. Around 1918, Hardy visits Ramanujan at a nursing home in the London suburbs. The Indian genius lay there, ill with tuberculosis. Hardy strikes up a conversation. He says the number of the taxi he rode in 1729 seemed rather dull, and he hoped it wasn't a bad omen. Ramanujan replies, "No, it's a very interesting number. It's the smallest number expressible as a sum of 2 cubes in 2 different ways. Written as an equation, it looks like this. 1729 is 1 cubed plus 12 cubed, and at the same time 9 cubed plus 10 cubed. Checking it is grade school arithmetic. 1 plus 1728, and 729 plus 1000, both equal 1729. Turn the anecdote around and a question remains. Once it got a lawyer, even the dull 1729 became a star, so is there really any truly featureless, boring number out there at all?" Surprisingly, mathematicians pass around an answer that's half joke, half serious. There isn't a single boring number, and you can prove it. Chapter 1. Let's watch that suspicious proof for ourselves, starting with the most brazen theorem in the world. In 1945, a short note by Beckenbach appears in an American mathematics journal. It's the oldest record of this paradox in print. The proof follows. Step 1. Assume there is at least one uninteresting number, that is, a boring number. Step 2. Line them up from smallest to largest. As long as the row of natural numbers isn't empty, there must be a front of the line. Step 3. Call that front of the line number m. M is the smallest boring number in the world. Step 4. But wait. The smallest boring number? Isn't that a rare title, the only one among infinitely many numbers? Which means m is an interesting number. Step 5. A contradiction. M was chosen as a boring number, yet it turned out to be interesting. The only place that could be wrong is the step 1 assumption. Therefore, there are no boring numbers. This argument spread far and wide after Martin Gardner featured it in his famous column in 1958. Though he presented it not as a theorem, but as one item in a collection of fallacies. So the official verdict is that it's wrong somewhere. But pinning down where is hard, because this proof is assembled from 3 parts. Let's take the parts apart one by one and inspect them, starting with the first part. Let's go back to 1729. Until we heard the defense, 1729 looked ordinary to anyone. Not a square, not a prime, even Hardy called it a dull number. Ramanujan's logic goes like this. Some numbers can be written as a sum of 2 cubes. Take 9, which is 1 cubed plus 2 cubed. But almost all such numbers have only one way. 1729 is the smallest number that has 2 such ways. Rather than arguing in words, let's have the computer count up to 25,000. There are 373 numbers that are a sum of 2 cubes, and among them exactly 4 have 2 ways. Those 4 are 1729, 4104, 13832, 20683, and standing at the very front is 1729. The picture on the left shows a different angle. The curve x cubed plus y cubed equals 1729 passes through integer coordinates exactly twice. 3 asides. First, this property was in fact already recorded by Frenicle de Bessy back in 1657. Even so, that it came out on the spot from a sickbed is a legendary scene in itself. Second, the condition of positive cubes matters. If you allow negatives, then 91 is 3 cubed plus 4 cubed, and also 6 cubed plus negative 5 cubed, so 91 becomes the first to have 2 ways. Third, 1729's resume has other lines too. Its prime factorization is 7 times 13 times 19. Add up its digits. 1 plus 7 plus 2 plus 9 is 19. And 1729 is divisible by that very 19, with the quotient 91 being the product of the 2 remaining prime factors. To sum up, the first part gets a half pass. The definition may be fuzzy, but the act of defending a number by saying it has such and such a feature is clearly possible. So a question arises. Can every number be defended the way 1729 was? Or is there a number that even a lawyer would throw up their hands at? Let's measure it ourselves. We can't measure interesting precisely, but we can imitate it. We build a list of criteria out of 11 features that mathematicians love. We call how many of these a number passes its interestingness score, and we grade every number from 1 to 1000. Will a boring number scoring 0 actually turn up? The scorecard is brutal. Of the 1,660 of them, 66% score 0, 290 score 1, and the celebrities scoring 3 or more come to just 11 in all. The top score is the number 1, being a square, a cube, a triangular number, a Fibonacci number, and a factorial all at once. It racks up a whopping 9 points. 2 follows with 7 points and 6 with 5. And then the long-awaited first 018. It's the first number to slip past all 11 criteria. We've found our candidate for the most boring number in the world. But before we raise a toast, 2 things already look suspicious. First, put a lawyer on 18 and out it comes. 18 is the only natural number that equals exactly twice its own digit sum 1 plus 8. It scores 0 not because it's boring but because there are only 11 criteria. The second is nastier. Just now, 18 became the star of a diagram in this very video for being the smallest number to score 0, earning a red circle and even an arrow. It sounds like a joke, but exactly this has played out for real over and over. Let me show you just 3 documented cases. Case 1, the fate of 39. In David Wells's 1986 The Penguin Dictionary of Curious and Interesting Numbers, the entry for 39 reads like this. The instant it was named the poster child of boredom, it got enshrined in a dictionary. As a footnote, in the 1997 revised edition the title is said to have passed to 51. Case 2. The curse of 11,630. Mathematicians have the OEIS, the Online Encyclopedia of Integer Sequences, a catalog of some 390,000 entries. In 2009, Johnston combed through some 150,000 sequences and announced that 11630 is the smallest number that appears in no sequence at all. What came next was predictable. Once it made news, 11,630 showed up in several sequences, and the crown passed through 12,407 and 14,228, and now it's moved on to 20067. Case 3, Sloan's Gap. In 2011, 3 researchers plotted the appearance counts from 1 to 10,000 as a scatter plot, and the shock was in its shape. The dots split into 2 clouds with an empty space between them. The upper one is the celebrity district, primes, squares, and the like. But this gap alone can't be explained by any theory. In a random database, no gap appears. The culprit wasn't mathematics, it was people. A number that's studied more shows up more, grows more famous, and so gets studied more, a feedback loop. One ironic scene. In 2009, the legendary 1729 appeared in 380 sequences, while its neighbor 1728 appeared in 622. Being 12 cubed, it's irregular in combinatorics. The verdict on the first part. Interesting isn't a fixed property. It's closer to an event that happens between a number and people. For now, we set it aside as suspect. On to the second part. A line of natural numbers always has a front of the line, to give the verdict up front. This part is genuine. In mathematics it's called the well-ordering principle. It seems too obvious, but this is actually a privilege unique to the natural numbers. Step over to the neighboring world of positive fractions and it already collapses. Try to find the smallest positive fraction. 1 over 4 is smaller than 1 over 2, and 1 over 200 is smaller than 1 over 100. Whatever candidate you pick, its half is always smaller, so there's no smallest. The natural numbers are floored at 1 and stand spaced apart, so you can't descend downward forever. That's why a smallest one must exist. The engine is genuine. Since the engine is genuine, let's watch the proof at work. Apply the 11 criteria from 1 to 50 and 10 numbers score 0. What if, each round, we promote the smallest boring number? In round 1, 18 takes the crown and gets promoted. The seat then passes to 20, and in round 2 by the same logic, 20 is promoted too. 26, 30, 35, 38 vanish one after another, and in round 7 that very 39 from Wells's dictionary meets the same fate. In just 10 rounds boring numbers go extinct. But look at the colors in the trick shows. Blue cells are numbers made interesting by passing a criterion. Yellow cells are numbers made interesting by the title alone, without passing a single one. What that title points to changes every round. 18's justification vanished the moment round 1 ended. The rules of the game change with every round. The culprit's outline is clear. Let's go make the arrest. The parts inspection is in. The well-ordering principle is genuine, and the third part is acceptable too. What's left is the first part, interesting itself. The culprit is hiding here. The well-ordering principle isn't all-powerful. It applies only to a collection where it's cleanly settled which numbers belong. The even numbers less than 100 are such a collection. But what about the boring numbers? By the 11 criteria, 18 is boring. Add one more and it's interesting. And to anyone who has watched this far, it's already an interesting number. A collection whose membership sloshes around depending on the person and the moment is not a mathematical set. There was nothing for the well-ordering principle to be applied to. The proof already ran aground at step 2. And yet it seemed plausible because of a swap at step 4. From steps 1 through 3, interesting is treated like a fixed list of criteria. Then, at the decisive step 4, it quietly slips in a new criterion that wasn't on the list, the smallest boring number. It amounts to moving the goalposts and then declaring a goal. Borrowing Quine's taxonomy, this kind is a falsitical paradox. Its conclusion is false and it does contain an error, but the error is so subtle that the paradox is worth chewing over. This diagnosis is confirmed by 2 thought experiments. Experiment 1, if we nail interesting down to passing a criterion, then the smallest boring number is just 18. No contradiction, no explosion. Experiment 2, conversely, if we let the definition swallow itself, it becomes a real bomb. Let's sharpen interesting precisely, as can be pinned down in a few words. The smallest number that cannot be described in 20 words. Count the words, just 10. We just described a number that supposedly cannot be described. This is exactly the Berry paradox. And from here it turns into a real affair that runs all the way to Gödel and Turing. The interesting number paradox is, in effect, its mild version. And OS adds one final lesson. Even if you swap interestingness for a count of appearances, as long as that metric is built out of people's attention, the problem never goes away. The grand finale. The theorem has collapsed. Every number is interesting was never a mathematical theorem. It was a cleverly wrapped joke. But there's a reason this joke has been loved for nearly 80 years. As a theorem, its conclusion is fake, yet as an attitude it's genuine. The year after Ramanujan died at the age of 32, Hardy left this line in his obituary. Every positive integer was one of his personal friends. This famous line has a postscript. Hardy's draft only said, as someone once remarked, but by the time it went through the proofs the attribution had turned into Littlewood. One footnote. The number Hardy called dull now lives in fiction. The animated series Futurama calls the robot Bender its 1729th son, and puts whole number 1729 on a spaceship. In the movie, a taxi numbered 875393919 drives by 2. It's the smallest number that can be written as a sum of 2 cubes in 3 different ways. The taxi is still running. We can't prove that every number is interesting, but betting that a boring-looking number simply hasn't met its lawyer yet, that's a pretty safe bet. Next time you take a taxi, take a look at the plate. First it'll seem dull, but the moment you ask it what makes it special, the one and only conclusion of this paradox kicks in. If you enjoyed today's journey, please support us with a subscribe and a like. See you at the next Odyssey here at ELLS Lab.